In the first part of Theory of Conjugate Functions or Algebraic Couples with a preliminary and elementary essay on algebra as the science of pure time, the Irish mathematician William Rowan Hamilton developed what we might call an axiomatic basis for the real numbers. In the second part, read on June 1, 1835, Hamilton developed an axiomatic basis for the complex numbers. Hamilton introduced algebraic couples A, B, where we can regard A and B as real numbers. We'll simplify Hamilton's notation but preserve his essential ideas. So given two algebraic couples, Hamilton established a number of key properties such as their sum, the decomposition as a sum, and what we can view today as a scalar multiplication, the last of which we can, by definition, rewrite as a quotient. And we do require that this denominator not have both components equal to 0. Next, by identifying the real number c with the number couple c0, we can write our quotient as, and we can rewrite this as, and this allows Hamilton to make other claims about other quotients. For example, next, Hamilton made some other claims, and while he didn't provide a proof of these claims, they are straightforward to prove from his axiomatic basis. Now, while we've defined one particular product of these algebraic couples, what about a general product? To find this product, Hamilton broke it down as follows. First of all, A1, A2, we can rewrite that as A10 plus 0A2, and this allows us to expand this product as and since if we multiply by a couple whose second component is 0, that's really just a scalar multiplication, then this first product, A10 by B1, B2, is the scalar multiplication by A1. Similarly, this second couple, B1, B2, can be expressed as a sum, and so that means we can expand this second product as, and here again we have multiplication by a couple whose second component is 0, so that's going to be a scalar multiplication by B1, and that gives us, and so the only remaining question is, what happens when you multiply two couples where the first component is 0? So suppose we multiply two algebraic couples whose first component is 0, and by assumption we'll get another algebraic couple. Now, by previously established properties, C1 and C2 have to be proportional to the product of A and B. This has to be true because if we take the scalar multiple of the product, by assumption the product is some algebraic couple C1, C2, and by the scalar multiplication we get KC1, KC2. But on the other hand, if we find the scalar multiple of the first factor, and then multiply it by the second, we get, and again we should get the same thing, and what that means is that C1 and C2 have to be directly proportional to A, because when we scale A by a factor of K, we also scale the two components. And by the same argument, C1 and C2 are also directly proportional to B, and so they're proportional to the product, A and B. So that means we only have to worry about the product 0, 1 times 0, 1, and then everything else will be a scaling. So let's assume this is a couple gamma 1, gamma 2. To decide what these are, Hamilton considered four quotients. C0 divided by C0, 0C divided by C0, 0C divided by 0C, and C0 divided by 0C. So suppose this quotient C0 divided by C0 equals x. So remember, by definition, this quotient corresponds to the product, and in this case that product will be C0 times xy, and this is a scalar multiplication by c, so it's got to be cx cy. And if we compare our components, x has to be 1 and y has to be 0. And so this quotient has to be 1, 0. By essentially the same reasoning, we can find the next two quotients as well. But what about that third quotient? So proceeding as before, we can rewrite this as a multiplication, and then we can expand out that multiplication. And remember, we assumed that 0, 1 times 0, 1 is gamma 1, gamma 2, and so that means this product is going to be gamma 1 cy, gamma 2 cy. And if we compare our components, we get a system of equations in x and y, and if we solve them, we get and note that if we want this quotient to be possible, gamma 1 can't be 0, but gamma 2 might be. So how can we find gamma 1, gamma 2? Well, again, let's go back to a general quotient, AB divided by CD equal to XY. Now, if we want this quotient to be defined for all algebraic couples except for CD 0, 0, then we have a system of equations. So again, rewriting our quotient as a product and expanding out the product, comparing the coefficients gives us a system of equations. And we'd like this system of equations to have a unique solution, x, y. And we find that if we try to solve this system of equations for x and y, we end up having to divide by the expression. And so we need to require that this expression not be 0. So with a little bit of algebra, Hamilton noted that this expression could be rewritten as, which is to say, a square minus something else. Now, if this gamma 1 plus 1/4 gamma 2 squared is positive, then there will be values c and d that will make this equal to 0, and we won't have a unique quotient. If this is equal to 0 and gamma 2 isn't 0, we have the same problem. So if it's 0 and gamma 2 is 0, then gamma 1 has to be 0. But remember, we found this quotient required dividing by gamma 1, so we can't allow this choice. Consequently, we can guarantee a unique solution provided that gamma 1 minus 1/4 gamma 2 squared is strictly negative. To do that, it's necessary for gamma 1 to be negative. So again, returning to our earlier problem, we can define this product to be gamma 1, gamma 2, where gamma 1 is negative, but we also have this quotient, so the simplest possible choice would be to make gamma 1 equal negative 1 and gamma 2 equal to 0. And this gives us the product, which is equivalent to stating that the square root of the number coupled negative 1, 0 is 0, 1. But since the number coupled negative 1, 0 was identified with the real number negative 1, this also says that the square root of negative 1 is this number couple, giving us the correspondence 0, 1 as the complex unit.